Hi everyone, and welcome back to this series of application of WEKA as a machine learning tool to assess different power system assets. In the last tutorial, we talked about 1D signal, okay? And we said that for 1D signal, we need to extract some feature from them, and we did some statistical features like the kurtosis and the skewness, and we use this as our feature vector. Now, what if I have a 2D signal? 2D signal means we have an image. How we can classify the image? And today we will be working on this problem is how to classify the degree of pollution on the surface of the insulator using their images. Okay. But before that, as we do, let me give you a little bit of background so that you understand what is this problem and why it is important. Now, when the insulators are polluted, the pollutions, especially if the insulators are close to the sea or close to some industrial area, they will have certain minerals in them. And whenever there is some humidity, drizzle, then those minerals, those salts will start to dissolve, will make a conductive electrolyte on the surface of the insulator, which eventually can lead to flashover. Okay, so this is a serious problem in outdoor insulators. Now, how to quantify the degree of pollution? We have two metrics. One called the equivalent salt deposit density, the ESDD. The other one is the non-soluble deposit density, or the NSDD. The first one will tell us or to quantify the amount of conductive material in the pollutant. And this will need to dissolve those salts or minerals and then measure their conductivity, and there is a standard how to convert this conductivity into ESDD, which is basically it's a milligram per centimeter square, how much milligram of the salt with respect to the surface area of the insulator. But in this problem, we'll try to actually classify the NSDD. And how we measure the NSDD, practically, basically what we do, we wash the insulators, okay, and we collect this pollutant, and then using filters, we will try to uh, uh, separate this non-soluble material. It's an inert material. It's like the dust, the sand, nothing that is conductive. So we'll try to have this material, and then we will take its weight, and we divide the mass of this pollution we collect by the surface area. We get the NSDD, which has the same unit, milligram per centimeter square. But here in the ESDD, it is more of the conductive amount of the pollutant, and here the NSDD is the inert amount. Okay. Now in our problem, we want to quantify the second, the NSDD, using images. Okay, how we do that? We prepared three different levels of this pollutant. We use a kaolin as our main inert material. Okay, and we have it at different levels to get these four different levels of pollution. The first one is called clean, from zero to uh, 0 to 0.357 milligram per centimeter square. Level 1, which is between 0.357 to 0.714. Level 2, 0.714 to 1.07, and so on. For level 3 is higher than 1.07 milligram per centimeter square. Okay, so we prepare a solution with the kaolin. We dip the insulator inside this kaolin. Now the 5 gram will give me this level, this will give me this level, and this will give me the last level. And then we hang the insulator like this, leave it until it is dry, and then take the image. Okay, now when we take the image, this is the image of the insulators. How I can extract features, because I cannot feed the whole image as it is. We mentioned that we can do that if we are using deep learning. In deep learning, we can just use the image as it is. Okay. Here you cannot do that. Here you have to extract some features from the signals. Now, what the features we try, we convert the image into the black white image, and then we something called the tonal value. The tonal value is the brightness of the image. Okay, the pixels of the image, how bright it is, these images. And then what we do, we extracted two features. Now this is the distribution of the tonal value. Here in the y-axis is the pixel density, how many pixels with this level. Okay, so this is the distribution. So we take the area of the first 60, 70 tonal values, which is the dark side. We take the area, this area, how much this area, and we take the global mean of the whole distribution, as you can see here. So let me give you an example. So for example, here for a clean insulator, it's a bit dark. So this is the area, the area of the first like 70 tonal is 0.131, and the global mean is 92.7. Now, if we have a polluted insulator, okay, so for the polluted insulator, you can see here it becomes more whitish because this is the nature of the pollutant. So here we see that a reduction in the area because this blackish color has much less number of pixel compared to this one. So this will be much less, and the global mean will be higher because we have here more insulator, a more whitish color here, so we will have a larger global mean. So this is values for the clean. This is for the global mean, and this is for the area. This is level 1, this is level 2, and this is level 3, and these are these corresponding values. So we have 24 images for each class, and now we want to classify them. So let's go and use our WEKA to use this feature vector. So we'll go to as usual our Explorer, and we'll open the file that we prepared, and we will just have a look to this file, and then we will start the classifications. So it is the NSDT classification. Here we'll CSV, and this is the file we have open. Okay, so we have the global mean. Now we understand what is the global mean. We have the area, okay, and we have the classes. So we have 4 classes, and this is clean, level 1, level 2, level 3. So as the level increases, they have more pollution. Okay, now let's visualize the data before we do any classification here. So let me look here. So let's have the area here. Let's, for example, here. Now we look here. So this is the x-axis is the global mean. The y-axis is the area. So here we have the clean is very far away from the other classes. The other classes, they are somehow, there is intersection between them. They are somehow overlapping between them. So you are expecting that for the clean it will be like 100%, and the level 3 is a bit also far. So we expect that the overlap is between level 1 and level 2. These are the ones that we expect to see some overlap. So it is very good to visualize the data, and you will get some sense about your results, especially when your feature vector is small, like 2 numbers. So then you can easily see in 2D graph how the classes are clustered together. Okay. So we have an idea now about the data. So let's go for the classification. Choose. Let's use our ANN. Okay. Let me start with one hidden layer. Okay. And let's class start. So we get 80% here. Now, when we look here, as expected, the clean, we have the 24 classes cases are all classified correctly. Now, here we can see that level 1 and 2, there is a lot of overlap between them, and there's a lot of confusion between them. And even there are some cases confused with the last one, but there is no much, there is little bit of confusion between level 1 and level 1, the clean one. Okay. Now, We know that usually we don't get good results with one hidden layer. So let's increase it to 2 hidden layer and see what we'll get here. Okay, and start. So this is a jump, like 7% jump here. And of course, this class, the clean one is 100%, the true positive there. Now, the problem is in level 2. In level 2, we have only 62.5%. The others are all above 90%. So this is overall 87.5. Okay, let's see what if we increase the header layer to 3. Although I don't recommend to keep on increasing the header layer, because with such small number of data, you will have a very, what we call, overfitting model. That model only fit to this data. Okay, so let's start here. So, okay, further improvement 2% here. And reduction in the last one was above 90. Now it is 87%. So always there's some sort of compromise. Okay, so this is the ANN. Let's go and check another classifier. Let me do the KNN, and I will start with KNN1. Start. Get 92.7%, and actually this is the highest I could got using this data. And we here again with everyone is above 90% except the last one. It is 87.5%. Okay, so this is really very good results, 92.7%. Especially this is a 4-class problem. If we increase the KN to 3, you will see that there is a reduction. So not always increasing the KNN, the number of neighbors that you check the distance is a good thing or improves. So this is drops a little bit to 89%. If you go to KNN 5, okay, start. 90%, but still KNN1 is the best. Okay, if you go and choose another classifier from, let's say, trees, let's say the G48, start, we get 89.5%. So they are getting in the 90s, early 90, 89%. That is the classification accuracy, which is pretty good for this small number of data sets. So what we are what I want to say here now, for the image, the whole image now is changed for us into 2 numbers using the tonal value, the global mean, and the area of the first 70 tonal values, the area of the distribution there. So the whole image now is just two numbers. So of course, we lost a lot of features here, because you cannot say that the whole image can be only represented 100% by these 2 numbers, but those 2 numbers reflect sort of the features, or the most important feature of the image, which is the brightness and the darkness of the image, which is related to the pollution level. Now, this is the ultimate thing we achieved? No, of course. We remember we did that under very controlled conditions. The distance between the camera and the insulator was fixed. The lighting condition was fixed. And I can tell you about this project. When we took the samples outside the lab and we took the images under a clear sunny day, we try to classify, we got very bad results. Why? Because now the whole lightning condition, because remember what we did, basically we took the tonal value. Now the tonal value will be totally different. The brightness of the image will be different when you change the lighting conditions. Okay, so then you have to do sort of some arrangement. What we did in this specific example, we took an offset. We found that the whole tonal value has changed by an offset because of the sun. We subtract that offset, and then we got good results. But again, the best thing when you deal with images is the deep learning, actually. But the drawback, you have to feed tens and thousands of pictures to do that. But with the machine learning, only few images, we could get very good results. Thank you for joining me in this tutorial, and looking forward to meet you in the future in some other tutorials.